Picture this. You stumble into the kitchen first thing in the morning. You plug your coffee maker into the wall socket to get the water heating up, and then you turn around, grab a magnetic clip, and just snap a grocery list onto the refrigerator door.
Right, just totally normal morning stuff.
Yeah, exactly. Two incredibly mundane actions. You do them without even thinking.
Yeah.
But if you were to ask most people what connects those two specific events, I mean, the answer would probably be absolutely nothing.
Right, because you're interacting with what feels like two completely different features of the physical universe.
Exactly. But today's deep dive is all about how they are actually the exact same thing. Welcome to the deep dive, by the way. Our mission today, as always, is to demystify the science behind everyday phenomena. And, we're assuming you have absolutely zero science background.
None required. Because for centuries, I mean, the greatest scientific minds on Earth would have completely agreed with you. They placed that spark from the wall socket and, the invisible pull of a fridge magnet into totally separate categories.
Like different drawers in the scientific filing cabinet.
Exactly. Like one is this electrical current that flows through metal, generates heat, makes light. And the other is just this strange property of certain rocks or metals that pull on steel. They just didn't seem to belong in the same conversation at all.
I mean, it really does feel like comparing a thunderstorm to a compass needle. There's just zero intuitive overlap there.
None. But the reality, and really the focal point of the source material we're diving into today, is that the spark in your wall and the snap of that magnet are the exact same force.
Which is wild to think about.
It really is.
Yeah.
We're going to trace this whole historical detective story of how humanity actually figured this out. It's this crazy journey of accidental discoveries and massive conceptual leaps that finally unified these forces and, in the process, literally built the modern world.
So to really wrap our heads around that unification, we should probably start by looking at how these forces operate in isolation, right? Like starting with just electricity.
Yeah, that's the best place to start. If we strip away all the complex stuff, the copper wires, circuit boards, the whole power grid electricity, basically comes down to a fundamental property of matter that we call charge.
Okay, charge.
Right. It's this built-in characteristic of the universe.
Yeah.
And it operates on a very strict rule of polarity, positives and negatives. The golden rule is charges push away from each other and opposite charges are drawn together.
Opposites attract, likes repel. We see this play out even at the subatomic level, right? Like if we look at a basic atom.
Yeah, exactly. You have these positively charged protons that are basically anchored right in the center, in the nucleus.
Right.
And then surrounding that nucleus, you've got these negatively charged electrons that are just in constant motion, buzzing around.
And normally the universe kind of prefers equilibrium, right? So the positive protons and the negative electrons, they just balance each other out. The atom is neutral.
Exactly. And that neutrality means everything is quiet. Nothing happens. The dramatic, flashy stuff we associate with electricity, that only happens when we somehow disturb that balance.
Right, when we force a separation.
Yeah, because once you force a separation of charge, the system desperately wants to correct itself.
You know what this reminds me of? It's like dragging your feet across a carpet in the middle of winter.
Oh, perfect analogy. Yes.
Because the friction of your socks rubbing against those synthetic fibers, it's actually doing physical work. You are literally scraping loosely held electrons off the carpet and hoarding them on your own body.
Right. You become this walking vessel of negative charge.
Yeah. And because charges repel, all those surplus electrons on your skin and your clothes are frantically pushing against one another. They want to escape.
They are seeking a path to ground, a way to just get back to equilibrium.
And then you reach for the metal doorknob.
Yep. When your hand gets close enough, you provide that path. The air between your finger and the metal literally breaks down for a fraction of a second and zap. All those electrons just surge across the gap.
And you feel the shock. You see the little spark. And the balance is restored. It's electricity in its most raw, chaotic form.
Exactly.
And, I mean, lightning is just that exact same carpet shock, just scaled up to terrifying atmospheric proportions, right?
That is exactly what it is. It's just the friction of ice and water inside a storm cloud separating the charges. It builds up these massive static imbalances until the air itself tears apart to let the electrons jump to the ground.
Wow. But, a chaotic momentary spark isn't exactly useful if you want to, power a reading lamp or run a hospital.
Right. No. For that, we need something controlled, a continuous flow. We need an electric current.
Okay, so how do we get from a spark to a current?
Well, a current requires a conductor, something that allows those electrons to move freely. And copper is sort of our gold standard for this.
Because of how its atoms are structured.
Yeah, the atomic structure of copper is kind of like a lattice, and it's filled with this sea of electrons that aren't really tightly bound to any single atom. They could just sort of drift from one atom to the next.
Gotcha.
But to get them to actually flow in a unified direction to do work, we have to apply pressure.
And this is where our source text uses a really brilliant analogy that I think helps visualize the mechanism, the water pipe analogy.
I love the pipe analogy. It totally clarifies the difference between the electrons themselves and the energy that they're carrying.
Right, because normally we think of a wire as like an empty tube waiting for electricity to flow through it.
But you have to think of the copper wire as a rigid pipe that is already packed completely full of water. The water represents those loose electrons naturally just hanging out in the metal.
Okay, so the pipe is already full.
Completely full. So when you connect a battery or plug into a power source, you're essentially applying physical pressure to one end of that pipe. And in physics, we call that electrical pressure voltage.
Okay, wait, let me push back on this slightly. Because this is where the whole mechanism gets a little counterintuitive for me.
Sure, go for it.
The source notes that the actual individual electrons drift through the wire incredibly slowly. Like, we were talking fractions of a millimeter per second.
Very slow. Sluggish, even.
Right. So if the electrons are moving like this sluggish river, why does my kitchen light turn on the absolute millisecond I flick the switch? Like, shouldn't there be a delay while those slow-moving electrons travel from the switch on the wall all the way up to the ceiling fixture?
Okay. It comes right back to the pipe being entirely full.
Oh, because there's no empty space.
Exactly. Imagine you have a mile-long pipe packed with water. If you force just one extra drop into your end, a different drop of water instantly falls out of the far end, right?
Oh, wow. Okay, yeah.
The voltage, that electrical pressure, it's pushing on the entire column of electrons simultaneously. So the mechanical nudge, that pressure wave, it propagates through the wire at a massive speed, like a significant fraction of the speed of light.
So the energy arrives instantly, even though the specific electron that just went through the switch might take, like, hours to actually reach the light bulb.
You nailed it. You aren't waiting for a delivery truck to drive from the switch to the bulb. The switch just shoves the back of the line, and the front of the line immediately shoves into the filament of the light bulb, creating heat and light.
Okay, that makes perfect sense. So that's the electrical side of the equation. Moving charges, voltage applying pressure, currents flowing through conductors.
Right.
Now let's contrast that with how science historically understood magnetism, because they were in different drawers, remember?
Right, totally different drawer. Magnetism was viewed through the lens of, like, lodestones and iron. Permanent magnets.
Magnets have a north pole and a south pole?
Right, and the mechanical rules actually mirror electrical charges. Opposites attract, likes repel. North pulls south, but north violently pushes away another north.
And a magnet projects its influence into the space around it, which is the magnetic field.
Exactly. You can actually visualize it if you've ever sprinkled iron filings on a piece of paper over a bar magnet.
Oh yeah, in like middle school science class.
Right. The filings arrange themselves into those distinct looping lines connecting the north and south poles. Those are the invisible lines of magnetic force.
And the Earth itself is just a giant magnet, right? Generating a weak magnetic field that stretches way out into space.
Which is exactly why a compass works. A compass needle is just a tiny lightweight magnet balanced on a pin. It swings freely until its own poles align with the magnetic field lines of the Earth.
Okay, so that brings us up to roughly the early 19th century. We have the electrical phenomenon, sparks, currents, voltage, and we have the magnetic phenomenon, fields, compasses, lodestones.
Operating in completely separate scientific domains.
So what causes the collision? How do these two drawers finally get mixed up?
The collision happens in 1820 over in Copenhagen. It's an amazing story. There's a Danish physicist named Hans Christian Ørsted, and he's just delivering a normal lecture to his students. The setup on his bench is super simple. He has a battery connected to a wire, and he's getting ready to demonstrate how an electric current can heat up the metal.
So just a routine demonstration of electrical resistance?
Completely routine. Nothing groundbreaking planned.
Yeah.
But by pure chance, a compass just happens to be sitting on the bench near the wire.
Oh, wow. Just left there by
No,
accident.
just sitting there. And when Ørsted closes the circuit and that electric current begins to flow through the wire, he notices something out of the corner of his eye.
Don't tell me.
The compass needle twitches. It actually deflects away from magnetic north.
Wait, really?
Yeah. So he breaks the circuit, stopping the current. The needle swings right back to its normal position. He connects the current again. The needle twitches again.
Okay, let's just isolate why this is such a profound observation. By simply running an electrical current through a standard copper wire, which, by the way, copper is not magnetic.
Not at all.
Right, so just by running current through this non-magnetic wire, he is invisibly reaching out and exerting a physical force on a magnet.
The implications were absolutely staggering to the scientific community. Ørsted had just proved that a moving electrical charge generates a magnetic field.
Electricity makes magnetism.
Exactly. And the shape of this new field was completely unexpected, too. The magnetic force didn't pull the compass needle straight toward the wire, and it didn't push it straight away either.
What did it do?
The magnetic field formed a circle around the wire. The current was basically creating this cylindrical aura of magnetism out of thin air.
Wait, so if an electric current generates a magnetic field, that means humans suddenly possess the ability to summon and control magnetism at will.
Yes, we were no longer reliant on just finding naturally occurring magnetic rocks.
We could just make it.
And this realization leads directly to the invention of the electromagnet.
Oh, of course.
Because, a single straight wire generates a relatively weak circular magnetic field. But engineers very quickly realized that if you take that wire and wrap it into a tight coil...
The fields combine.
Exactly. The magnetic fields from each loop stack on top of one another, compounding their strength.
Yeah.
If you run a strong current through a coiled wire, especially if you wrap it around an iron core, you generate a massively powerful magnetic field.
And crucially, you can turn it off. Like a permanent fridge magnet just exerts a constant pull. You can't switch it off. But an electromagnet is completely subservient to the voltage.
Which is incredibly useful.
It's how a scrapyard crane works, right? It lowers that massive metal disc onto a 2-ton car. They switch on the current to magnetically lock onto the steel, lift the car all the way across the yard, and then drop it simply by just cutting the electrical flow.
Exactly. Just breaking the circuit. And actually, the speakers you might be using to listen to this discussion right now rely on the exact same principle.
Really? Our speakers?
Yeah. Inside a standard speaker, there's a permanent magnet and a really lightweight coil of wire attached to a flexible cone.
Okay.
As your amplifier sends fluctuating electrical currents into that coil, the coil becomes an electromagnet with a rapidly shifting magnetic field. So it's pushing and pulling violently against the permanent magnet, which causes the cone to vibrate and push the air.
And those air pressure waves are the sound we hear.
Yep. Every nuance of the audio is really just a high-speed translation of Ørsted's twitching compass needle.
That is unbelievable. So, okay. Human curiosity proves that electricity can give birth to magnetism. I have to imagine the inevitable next question for physicists at the time was, does it work in reverse?
Naturally. If electricity makes magnetism, can magnetism make electricity?
Right.
And that question takes us to England in 1831 to Michael Faraday.
Ah, Faraday.
Faraday is one of the most fascinating figures in the entire history of science. He actually had very little formal mathematical training.
Really?
Yeah.
A physicist with no math background.
Basically, yeah. He began his career as a bookbinder's apprentice. He literally learned science by reading the science texts he was supposed to be binding for customers.
That is incredible.
So because of that background, he viewed the universe very visually, in terms of physical, mechanical interactions, rather than abstract equations.
Okay, so how does he test this reverse relationship?
He sets up a very logical physical experiment. He connects a coil of wire to a galvanometer, which is just a highly sensitive device for detecting electric current.
Right, to see if any electricity is flowing.
Then he takes a strong magnet and he just places it right next to the coil.
Hoping that the presence of the magnetic field will push the electrons through the wire and create a current.
Right, he fully expects a static, resting magnetic field to generate a continuous electrical current.
But let me guess.
He gets absolutely nothing.
Really?
The meter reads solid 0. The electrons in the wire remain stubbornly stationary. A stationary magnet does not induce electricity.
Wow, that must have felt like a massive dead end, like the symmetry was just broken.
It definitely could have been. But Faraday was famously persistent. While he was messing with the setup, he physically slides the magnet into the center of the wire coil.
Okay.
And in the exact moment the magnet is moving, the needle on his meter violently deflects.
A current surges.
Yes. But then he stops moving the magnet, leaving it just resting inside the coil. And the current instantly drops back to 0.
Wait.
Then he pulls the magnet back out, and the meter deflects again, this time in the opposite direction.
So the breakthrough is that the mere presence of a magnetic field is totally meaningless to an electron. It's the change in the magnetic field that matters.
The change is everything. When the magnetic field lines physically sweep across the copper wire, they exert this electromotive force on the electrons, literally shoving them down the pipe.
Wow.
We call this phenomenon electromagnetic induction. A fluctuating or moving magnetic field induces an electric current.
You know, understanding electromagnetic induction, it really fundamentally alters how you view modern infrastructure.
Oh, absolutely.
Because if you look past the massive cooling towers, the miles of steel pipes, the complex control rooms, almost every single power plant on Earth is basically just a scaled-up version of Faraday sliding a magnet into a coil.
It's so true. The sheer engineering scale totally obscures the underlying simplicity.
Like, walk us through it. Consider a coal or a natural gas power plant.
Okay, so the entire purpose of burning thousands of tons of fossil fuels is simply to boil water.
Right.
The boiling water generates high-pressure steam. That steam is directed through the blades of a massive turbine, which forces it to spin.
And attached to the shaft of that turbine.
It's an enormous heavy magnet nestled inside a cage of thick copper coils. As the steam spins the turbine, the magnet rotates.
And as it spins, its magnetic field lines are continuously sweeping through the stationary copper coils, physically pushing that sea of electrons down the wires, generating the voltage that eventually reaches my kitchen socket.
Exactly. And a nuclear power plant operates on the exact same principle.
Just a different way to boil water.
Precisely. Instead of burning coal, we split uranium atoms in a controlled chain reaction. The splitting atoms release tremendous heat, which boils the water, which makes the steam, which spins the turbine, which rotates the magnet.
It all comes back to the magnet.
Always. A hydroelectric dam just removes the steam entirely. It just uses the gravitational force of falling river water to spin the turbine. A wind turbine uses moving air to turn the blades, which spins the magnet.
It's kind of crazy when you think about it. We have spent trillions of dollars building incredibly elaborate machines just to rotate magnets near wires.
It really is the foundational engine of modern civilization. And actually, the symmetry of electromagnetic induction reveals another mechanical marvel, too.
Oh, really?
Yeah, we just detailed how physically rotating a generator produces an electric current, right?
Right, motion creates electricity.
What happens if we reverse the inputs on that exact same piece of machinery?
Okay, let me think. So instead of using steam to spin the magnet and extract electricity, we take a generator sitting perfectly still, and we pump a high-voltage electric current into its wire coils from an outside source.
Exactly. The current flows into the coils, which are resting inside a magnetic field. Now, as we learned from Ørsted earlier.
The new current generates its own powerful magnetic field.
Yes. So you now have two magnetic fields occupying the same space, and they push against each other violently.
Oh, wow.
The repulsive force physically shoves the coils, forcing the central shaft to rotate. We are turning electrical energy back into physical motion.
We've just described an electric motor?
Yep. A generator and an electric motor are mechanically identical devices. The only difference is the direction of the energy flow.
That is so elegant.
Isn't it? If you apply mechanical torque to the shaft, it acts as a generator and outputs electricity. If you apply electricity to the terminals, it acts as a motor and outputs mechanical torque.
So this symmetrical relationship powers everything from, like, the tiny vibration motor in your smartphone to the massive traction motors accelerating a subway train. Wires and magnets constantly translating motion into power and power back into motion.
It really is an elegant closed loop. But the final act of this scientific narrative, and honestly the part that fundamentally changes our understanding of the universe, happens when these forces detach from the copper wires and the iron magnets entirely.
Wait, they detach? How does that work?
Well, this brings us to the 1860s, and a Scottish physicist named James Clerk Maxwell.
Okay, Maxwell.
Now, unlike Faraday, who relied on that physical intuition and mechanical models, Maxwell was a mathematical visionary. His goal was to take Faraday's conceptual, invisible lines of force and describe them with rigorous mathematics.
Putting actual numbers to the fields.
Right. He synthesized decades of experimental data into a set of equations that definitively mapped how electric and magnetic fields behave and interact.
And the math revealed something new.
Something massive. Faraday had proved that a changing magnetic field gives birth to an electric field. Maxwell's equations demonstrated that the inverse is also undeniably true.
Meaning, A changing electric field gives birth to a magnetic field.
Exactly. And this reciprocal relationship has profound consequences. Imagine an electrical charge vibrating in space, creating a shifting electric field.
Okay, I'm picturing it.
According to Maxwell, this shifting electric field must create a corresponding magnetic field. But because this newly born magnetic field is also expanding and changing, Faraday's law dictates that it must immediately create a new electric field.
Which is also changing, so it creates another magnetic field.
You've got it. They're locked in a self-sustaining cycle. They no longer need a wire or a piece of metal to travel through. They literally leapfrog off one another, pushing each other forward through the total vacuum of empty space as a continuous ripple of energy.
Like a wave.
Yes. Maxwell had mathematically theorized an electromagnetic wave. And because he was working with such precise equations, he could actually calculate how fast this theoretical wave would propagate through space.
Oh, wow. So he could calculate the speed.
He took the known ratio of electric forces to magnetic forces, ran the numbers, and produced a velocity. The speed that emerged from his equations was approximately 300,000 kilometers per second.
Which I have a feeling isn't just a random number.
Not at all. It was a number that exactly matched the independently measured speed of light.
Oh my God.
Yeah. The mathematical alignment was just too perfect to be a coincidence. Maxwell realized that he hadn't just discovered a new type of wave. He had inadvertently discovered the fundamental nature of light itself.
That is just the ultimate conceptual leap.
Isn't it?
So you're telling me the sunlight providing warmth on a summer day, the glow of a distant galaxy, the flame of a candle, all of it is just an electromagnetic wave.
All of it.
It is the exact same forces that shock you on a carpet and stick your grocery list to your refrigerator, just dancing across the universe in a self-sustaining embrace.
Exactly. And visible light is really merely a narrow sliver of this phenomenon. The only difference is the frequency, basically, how fast those fields are vibrating.
So what happens if they vibrate at a different speed?
Well, if the electromagnetic wave vibrates at a lower frequency than visible light, we detect it as infrared heat or microwaves or the radio waves that carry data to our phones.
And if it vibrates faster?
At a much higher, more energetic frequency, it becomes ultraviolet light, X-rays, or gamma rays. The entire electromagnetic spectrum is just one continuous phenomenon.
It is difficult to overstate how unifying this is. I mean, think about it. Centuries of humanity observing static shocks on a carpet, navigating the oceans with compass needles, and gazing up at starlight.
3 entirely distinct realms of human experience.
Right, all just collapsing into a single, unified framework.
It's the realization that the universe is far more interconnected than our raw senses suggest. The rules governing the microscopic drift of electrons in a copper wire. They are intimately bound to the mechanics of light, traversing billions of light years of empty space.
Which honestly gives a profound weight to our daily routines. Like, you can trace a continuous chain of consequence.
Yeah, try it. Think about the coffee maker.
Okay, so when you plug in that coffee maker, you are completing a physical circuit. That circuit runs through the walls of your home, up to the transformers on your street, across miles of high-voltage transmission lines, and ultimately terminates at a power plant.
And at the heart of that plant is Michael Faraday's spinning magnet, continuously shoving electrons down the line through electromagnetic induction.
Right. And conceptually, the knowledge required to build that entire system traces backward to Maxwell's equations. And finally, all the way back to a Copenhagen lecture hall in 1820, where Hans Christian Ørsted noticed a compass needle twitching near a wire.
The modern era is entirely constructed upon our mastery of that single unified force.
It is just a remarkable chain of events.
It really is. However, the source material does leave us with one compelling exception to mull over.
Oh, really an exception?
Yeah. While Faraday's spinning magnets generate nearly all of the world's electricity, there is one major outlier on the modern power grid: solar panels.
Oh, the odd one out?
The odd one out. Think about it. A solar farm has no boilers, no steam, no turbines, and absolutely no spinning magnets.
None at all. They are entirely silent solid-state devices.
Exactly. Yet they manage to generate tremendous amounts of electrical current directly from sunlight.
Which is an electromagnetic wave.
Right. It raises a fascinating mechanical question. If the global standard for generating voltage requires the physical shoving of magnetic fields across copper coils, how exactly does a flat sheet of silicon sitting quietly on a roof manage to bypass Faraday's laws entirely?
That is a great question. How does trapped starlight translate directly into an electrical current without the magnet?
It is a brilliant puzzle to leave you with. Scientific unification answers massive historical questions, but it always sets the stage for the next deep mystery.
Absolutely. And as you go about your day-to-day, whether you're turning on a radio, checking a compass, or just enjoying the sunlight, take a moment to appreciate the invisible, unified dance of electromagnetism happening all around you. We really appreciate you joining us on this deep dive, and we'll catch you on the next one.